So hello everyone, welcome to the channel. So in this video I'm going to show you estimate the sulfur dioxide concentration from Ethiopia volcanic eruption using Sentinel-5P imagery in Google Earth engine. So now let's get started. So the volcanic eruptions are among the most significant natural sources of atmospheric trace gases and capable of injecting a large quantity of sulfur dioxide, ashes and other aerosol directly into the troposphere and stratosphere. Monitoring the sulfur dioxide emission during and after an eruption is essential for understanding the volcanic activity and assessing the atmospheric pollution, evaluating the aviation hazards, and estimating the potential climate impacts. So the sulfur dioxide plays a critical role in atmospheric chemistry. So once it is injected, can convert into a sulfate aerosol that influences the cloud formation and alters the incoming solar radiation and contributes to acid rain. Therefore, an accurate quantification and spatio-temporal assessment of sulfur dioxide concentrations are vital for volcanic hazard analysis and environmental monitoring. So the Hayli Gubbi volcano in Ethiopia experienced a significant eruption event between November 23 to 2025, releasing a large plumes of sulfur dioxide into the surrounding atmosphere due to the remote sensing location. So due to its remote location and hazardous condition during the eruption, the ground-based observations are limited. So in such a situation, a satellite-based remote sensing becomes the most reliable and operationally feasible method for continuous monitoring of volcanic gas emission. So among the available satellite emissions, the Sentinel-5P imagery provides a high-resolution global coverage of atmospheric sulfur dioxide, enabling us to track the plume movements and intensity variation and the dispersion pattern with daily temporal resolutions. So in this analysis, we're going to use our Earth engine to analyze and visualize and quantify the sulfur dioxide concentration during the Hayli Gubbi volcanic eruption. Sentinel-5P is a dataset utilized to generate monthly mean the sulfur dioxide layer, the eruption specific sulfur dioxide maps, and pre versus post eruption comparison. So a 500-kilometer buffer region around the volcanic vent is defined first as our region of interest to capture the full extent of the sulfur dioxide plumes. So this workflow is going to include the temporal filtering, pixel-wise statistical reduction and export of the time series data, and automate the generation of monthly and eruption phase of sulfur dioxide concentration maps. And also this particular workflow is highly scalable and can be applied to any volcanic system globally for emission monitoring and atmospheric analysis and the disaster response and aviation safeties and climate impact studies. So let me get back to Earth engine. So in the first step, we're going to define our region of interest. So our region of interest is our Hayli Gubbi volcano in Ethiopia. So first we're going to navigate to Ethiopia here. So the volcanoes exist towards the northern part of the study area. So that is our Ethiopia. So this particular Hayli Gubbi volcano, which lies in the northern part of the country here, you can able to see this particular one here. So let me navigate to this particular one here. So here you can able to see this particular vent in the volcanic vent. You can able to see that. So here we are currently visualizing the Hayli Gubbi volcanic system. So this particular volcanic system is characterized by its felsic to intermediate magma chemistry and producing eruption that is typically classified with an explosive volcanic type. So its eruptive behavior arises from its high viscosity magma enriched with silica, which tends to trap the volatiles like water vapor and sulfur gases. So as the pressure mounts beneath the surface, the system behaves like a sealed boiler, and once it breaches the crust, it releases energy in a brute and forceful burst. So this volcanic type is known for generating a pyroclastic density current and the block and ash flow, often sculpting the surrounding terrain with the vast tephra blankets. And if you're talking about the geological time scale, this particular eruption constructs a steep-sided stratovolcanic edifice and laid with an alternating pyroclast deposits and lava domes. So the landscape around the Hayli Gubbi often resembles palimpsests of geologic storytelling. So the old domes slumped like the tide, giants and fresh ash dramped across a slope, and the radial gullies carved by the lahars in the post-eruption monsoons. So in the next step, I'm going to use this particular tool here. So for example, I'm going to click this tool, and let me click this particular tool. So once you click that tool called add a marker, so I'm going to place a point over this particular volcano here. So once you place the point in the top section, we have this new variable called geometry, and in that I'm going to click this option, and here we have the latitude and longitude of this particular volcano here. So I'm going to copy it, and once you copy it, I'm going to close this, and I'm going to exceed this. So if you're talking about the dimensions and characteristics of this particular volcano, the elevation of this particular volcano is around elevation of around 493 meters above sea level. And this particular crater feature here, the summit area includes a graben, trench-like depression, which is formed by the tectonic stretching, and rather than a simple steep cone. So within this graben lies a volcanic cone featuring a crater roughly around 200 meters wide. And this particular volcano is of a shield volcano, meaning it has a broad and gentle sloping profile formed by the fluid lava flow, not the steep stratovolcano cone. Its slopes are relatively gentle and it covers a wider area instead of forming a sharp peak. So now let us head towards the analysis part here. So once you've placed a point over the volcano in this particular region of interest, so the next step, we're going to define our region of interest. So for that, I'm going to mention a variable called ROI is equals to earthengine.geometry.polygon, and I'm going to mention the latitude and longitude of this particular volcano, and I'm going to create a buffer of around 500 kilometers of buffer. So to do that, I'm going to mention dot buffer. So to create a buffer of 500 kilometer, I'm going to mention dot buffer, and I'm going to mention its unit in meters here, which is 5 lakhs. So which represents 500 kilometer buffer around the volcano. So next step, I'm going to define another variable called volcano point is equals to earthengine.geometry.point. So here I'm going to refer the latitude and longitude of the volcano. So basically we are creating two ROI. So one is of buffer ROI, that is 500 kilometer buffer, and second is we're going to create another point which indicating the volcano. And next step is we're going to define our analysis year and the eruption period. So for example, so the analysis year, I'm going to mention the variable analysis year is equals to 2025, and the eruption period, I'm going to mention it using variable eruption start is equals to 2025 November 23, and the variable where eruption ends, I'm going to mention as a variable eruption end is equals to 2025 November 25. And the next step, we have to set the visualization parameter for our the sulfur dioxide concentration. So to do that, I'm going to mention a variable called sulfur dioxide vis params, and the minimum I'm going to mention is 0, and the maximum I'm going to mention is 0.0005. It's just moles per meter square. And to set a color palette, so I'm going to mention the starting color to be black, and up to a red, which indicates the highest level of sulfur dioxide concentration during the time of the volcanic eruption. And the next step, we're going to define a function. So basically, we're going to create a function to get the monthly mean sulfur dioxide image for that area for the given year, that is 2025. And specifically, we are going to focus on November. So in order to observe the concentration variation, for example, we're going to visualize all the months in that particular year, and we're going to see any anomalies during this particular month in November where the eruptions has taken place. So to create that particular function, we're going to mention function get monthly SO2 and year. And next step, we're going to define a variable months equals to earthengine.list.sequence function. So we're going to mention the starting month and the end month. So one which indicates the January, and the 12 which indicates the December. And the next step is in the next step, we're going to create another function, another variable called variable monthly image is equals to months dot referring to this particular variable. And we're going to create this particular another function here dot map function month, and we're going to mention inside the function called variable start date is equals to earthengine dot date dot from y, that represents year, month and day. So dot from year, month, and day, and we're gonna mention the year as in this unit, and the month, and the one which represents the first day of the month here. So this particular represents the day. And next is we're going to define another variable called end date is equals to the start date, representing this particular variable, dot advance by 1, and the unit is in the month. So it's going to advance by for example, we're going to start by January, so it's going to advance by February and March, April, up to December. And next, we're going to use the offline data Sentinel-5P SO₂ imagery for historical analysis. So let me explain about this particular dataset here. So Sentinel-5P offline SO₂ offline sulfur dioxide. So the dataset availability is from 2018 to 2025, and the dataset provider is European Union ESA Copernicus, and this is the code to access this particular imagery. So this particular dataset, and these are the following set of bands that is available in this dataset here. So the resolution is around 1 kilometers. And here we have a variety of different bands that is available, starting with the sulfur dioxide column number density, and the sulfur dioxide column number density AMF, and cloud fractions, and solar azimuth angle. So we have a lot of different and last we have another band called sulfur dioxide column number density of 15 kilometer, and which is the unit of moles per meter square. So we're going to specifically use this particular band called sulfur dioxide column number density. So this is like ground level, the sulfur dioxide column density at ground level. So we're going to use this particular one here. So in case if you want to use it vertical column density at 15 kilometers of height, and in that situation you can use this particular band called column number density 15 kilometers. So in my analysis, I'm going to use this particular band called sulfur dioxide column number density of, and this particular one is the sulfur dioxide vertical column density at ground level. So calculated using a DOAS technique. And let me get back to Earth Engine. So first I'm going to define a variable called SO₂ collection is equals to Earth Engine dot image collection Copernicus S5P offline L3 sulfur dioxide, and I'm going to apply a filter dot filter date based on the start date and the end date of our analysis. And the next step, we're going to select the suitable band of our choice. For example, I'm going to mention dot select sulfur dioxide column number density. So we are selecting this particular band. You can able to see that. So that is SO₂ column number density. And in the next step, we're going to calculate the monthly mean. So to do that, I'm going to mention a variable called monthly mean is equals to the sulfur dioxide collection, referring to our image collection here. And in that, I'm going to apply this particular function dot mean function to acquire a monthly sulfur dioxide mean concentration. And to this mean sulfur dioxide concentration image, I'm going to mention this set of things here. For example, dot set year, the unit is an year, and dot set month, and dot set system time start, and start date dot millisecond function. So basically it's going to convert the date into a millisecond time format, like calendar range. And the next step, we're going to return it monthly means. And last, we're going to mention return Earth Engine dot image collection dot from image monthly image. So once we created a function to acquire the mean sulfur dioxide concentration, so the next step, we're going to create a time series chart for the sulfur dioxide concentration. So in order to visualize the changes in sulfur dioxide concentration over a period of time from January to December, so to create a time series chart for sulfur dioxide, we're going to create another function called create time series chart SO₂ collection, and we're going to mention the region, that is our study region. So next, we're going to define another variable called chart is equals to ui.chart.image.series, and image collection I'm going to mention is SO₂ collections, that is our Sentinel-5P sulfur dioxide, and the region, the study region, is going to be the region. And the statistical function we're going to apply is reducer. We're going to mention Earth Engine dot reducer dot mean function, and the scale I'm going to mention is 1000 meters, which is 1 kilometer of resolution, the resolution of Sentinel-5P imagery. And next property, it's going to mention system time start, and we're going to set additional options to this particular chart here. For example, the title I'm going to mention is monthly mean sulfur dioxide concentration over Hayli Gubbi region, plus the analysis year. So it's going to give us the analysis, the year. And the next is the h-axis. The title, it's going to be the date. In the format, it's going to be MMM. And the v-axis, the title is going to be sulfur dioxide column number density in moles per meter square. And you can mention other set of options like line width, point size in the series. And last, we're going to return the chart. So in the next step, we're going to export the monthly image to our drive. So to do that, I'm going to mention the function export monthly image. I'm going to mention is monthly SO₂, and the unit is in years. And inside this function, I'm going to mention the variable called months equals to starting month from January to December. And the next step, to export each monthly image, I'm going to mention monthly SO₂ dot evaluate function image. And inside, I'm going to mention for where a variable I is equals to 0, which represents January. And if I is lesser than 12, which it's going to giving a condition where the I should be lesser than 12 and I plus plus. So it's going to start from 0 to 11, that is from January to December. And next is we're going to mention a variable image is equals to earth engine dot image, and the image is I, and the variable month name is equals to months I. And the next is the export dot image dot drive. We're going to mention the image to be image, that is about sulfur dioxide. And description we're going to mention is sulfur dioxide plus the month name. So it's going to mention the month name here. If it is January, it's going to be January, and plus the year, so the period of our analysis, so it's going to be 2025. So it's going to give us both the sulfur dioxide concentration with the month name as well as the year. And the folder we're going to mention is earth engine dot sulfur dioxide analysis. And next is the file name prefix. I'm going to give it as a similar mentioned in the description here. And the region, it's going to be our ROI, that is our region of interest. And the scale is 1000 meters. And the coordinate reference system is EPSG 4326. And the max pixel value is 1:10⁻⁹. And the file format we're going to mention is a GeoTIFF. So now let us run this code and visualize our time series plot of our sulfur dioxide concentration. So we're going to click this option called run. So here you can able to visualize our monthly sulfur dioxide time series image. So we can able to see this is our sulfur dioxide column number density molecules per meter square, and this is our in months here. It's just given here, and there's monthly mean sulfur dioxide concentration over this volcanic area, and you can able to see the concentration of sulfur dioxide is kind of lower in during this set of months here, even till October. But at November, the concentration has significantly is higher than its normal levels. You can able to see from this graph here. So here you can clearly able to visualize the differences here. The concentration was previously was around 0.000025 was the concentration of sulfur dioxide in this area. But in the November, the concentration has been rose to more than 0.0004 molecules per meter square. So you can able to clearly view this anomaly here. Concentration of this sulfur dioxide was very higher, which indicates the volcanic eruption has taken place during this particular month. So now let me get back to Earth Engine. So in the next step, I'm going to export this time series data as a CSV. So to do that, I'm going to mention another function, export time series data monthly SO₂ region, and create a feature collection with the monthly statistics. So to do that, I'm going to mention a variable time series data is equals to monthly SO₂ dot map function image, and we're going to mention the variable stat is equals to image dot reduce region, and the reducer we're going to apply the statistical function called earth engine dot reducer dot mean function, and the geometry it's going to be the region, and the scale is around 1000 meters. So in the next step, we're going to define another variable called date is equals to earth engine dot date image dot get system time start, and return we're going to mention earth engine dot feature image. First we're going to mention the year, image dot get year, and similarly for month, and the date in the time format date dot format in year, month, and day, and the main sulfur dioxide concentration. The stats is stat dot get sulfur dioxide column number density, And last, the timestamp as a date dot millisecond format. It's going to give us in the calendar format. And last, to export to a Google Drive, we're going to mention is export.table.drive. And the collections is Earth Engine feature collection time series data, which represents this particular variable we have mentioned earlier here. And the description I'm going to mention is sulfur dioxide time series plus the analysis here, which is 2025. And the folder is GEE sulfur dioxide analysis, and the file format is in CSV. And the next step, it's going to be the main part of our analysis. So starting with, we're going to set the map centered to this particular volcano, Hayli Gubbi volcano. So to do that, we have used the previous coordinates with a specific zoom level. So you're going to mention map.set center, the latitude and longitude, and the zoom level. So the latitude and the longitude, and this is the zoom level. So in our first step, we're gonna to get the monthly sulfur dioxide data for our analysis here. So we're gonna mention the variable monthly SO2 equals to get monthly SO2 analysis here. It is our 2025. It's our analysis year, which we mentioned earlier, which is 2025. And we're gonna mention print monthly sulfur dioxide collection monthly SO2 representing this particular variable. So in the console section, you can able to see the monthly sulfur dioxide collection here. So here we have our features, 12 features. So in the feature, we're going to select the first image here. So the bands, we have the SO2 column number density, double float, the data type, and the coordinate reference system. And the properties, the month and system index, and the year, it is 2025. And in the next step, what we're going to do is we're going to display the November 2025 eruption period, the volcanic eruption, which the Hayli Gubbi volcanic eruption period. So to visualize it, I'm going to mention a variable November SO2 equals to monthly SO2 dot filter earth engine dot filter dot equals to the month, the unit, and the representing 11, it's November, and dot first function. So it's gonna give the first image in this image in this month. And to add this layer, we're gonna mention this map.add layer November SO2, and the for visualization parameter we're gonna mention is SO2 vis params, and we're gonna output the layer as November 2025 sulfur dioxide eruption period. So this is the point we marked earlier, and this is our Hayli Gubbi volcano. So we can be able to see that. And based on the point we created, it's going to create a buffer of 500 kilometer buffer here around this particular volcanic area. So this is the buffer we created, and this is the image. And now it's you can able to see this image here more clearly. And the red area, which indicates the highest level of sulfur dioxide concentration, where the concentration is very high. If the red value, if it is greater than or equals to 0.0005 moles per meter square, so it's going to be indicated in red color. So you can able to see if it's higher than this particular threshold value, it's going to be highlighted in red color. So from this image, you can clearly able to visualize it. So this is the volcanic area. Let me turn on the buffer. So here you can able to see that this is the buffer. So you can able to see this particular buffer here. So this is around this volcano. So this is the volcanic area. This is the volcanic area where the eruption has taken place. You can able to see the red. So, and also I can able to see this particular plumes travels from this particular area towards the eastern western part of the country. For example, in India, it travels towards in this direction towards the north eastern. It travels towards west as well as towards the eastern part of the countries. So the red traces, which clearly highlights its the travel of this particular sulfur dioxide here. You can able to see it more clearly. Let me turn on the buffer too. You can see that. And let me zoom in here. You can able to see the volcano here. So this is the volcano. And you can able to see the red spot, which indicates the sulfur dioxide eruption, the eruption which took place in this area. So this sulfur dioxide travels from Ethiopia towards India and also towards the neighbors of India, you can able to see this particular color, which clearly highlights its travel. So in the next step, what we're gonna do is we're gonna visualize this particular time series chart. So to do that, I'm gonna mention variable time series chart is equals to create a time series chart monthly SO₂ or based on our region of interest, and print as a monthly sulfur dioxide time series, and the time series chart of the variable we created earlier here. So you can able to see in the console section we have this monthly SO₂ time series data. And here you can able to see in this particular month the concentration of sulfur dioxide is very high compared to other periods in this month. Here you can able to see the drastic rise in the sulfur dioxide, which indicates the volcanic eruption in that particular period, which is between 2023 to 25 November 2025. And next we're gonna add the volcanic location and ROI boundary. So there is a buffer as well as the point which is shown you earlier, the red dot one. So for that I'm gonna mention map.add layer, volcanic point color red, and Hayli Gubbi volcano, and we're gonna add the region of interest, map.add layer ROI. The color it's gonna be blue, and fill color it's gonna be, we have seen that fill color, and the output the areas analysis region. There is a buffer which is we created earlier here. This is the buffer here. You can able to see the red color. And next to calculate and print the eruption period statistics, what we're gonna do is we're gonna create another variable called eruption sulfur dioxide is equals to earth engine dot image collection Copernicus S5P offline L3 SO₂. And we're gonna mention the filter date here. For example, dot filter date eruption start and the eruption end period. So we're gonna select this particular band dot select SO₂ column number density dot main function. And in the next step, we're gonna define another variable eruption stat is equals to eruption sulfur dioxide dot reduce region. So here we're gonna apply the statistical function, that is reducer earth engine dot reducer dot mean function, that to get a mean sulfur dioxide dot combine. We're gonna mention another reducer 2 is earth engine dot reducer dot max function. So we're going to get both the max sulfur dioxide as well as the mean sulfur dioxide concentration. And the geometry is our ROI, that is our buffer of 500 kilometer buffer. The scale is the 1000 meters. And we're going to output as sulfur dioxide statistics during the eruption, November 23 to 25, 2025 year. And eruption stats. So we're going to run this and take a look at this particular one. And here we have this sulfur dioxide statistics during eruption, and the objects we have column number density max is around 0.41. It's molecules, the molecules per meter square, which is pretty high compared to what we seen here. So you can able to see the values. Normally the values were around 0.0004, and now the values around highest is around 0.4, which is pretty higher. And the mean values it gives us to be around 0.0036 molecules per meter square. You can able to see the concentration in our study region based on the buffer we created. And next step, we're going to export the data to Google Drive. So to do that, I'm going to mention export a monthly image, monthly SO₂ analysis year. And next is we're going to mention export time series data, monthly SO₂ ROI. And in the next step, we're going to compare the pre and post eruption periods. So now let's compare the pre and post volcanic eruption in the study area. So to do that, we're going to mention a variable called pre-eruption is equals to earth engine dot image collection Copernicus S5P offline L3 SO₂. And we're going to filter it based on the specific time period here. For example, I'm going to filter dot filter date 2025 October 2 to 2025 October 28. And I'm going to select a band dot select SO₂ column number density. I'm going to select this particular band here, and I'm going to apply a median function to it, or even you can select the mean function. And we mentioned as a median function, so you can also select mean function if you required. So in my case, I'm going to use the median function. And similarly, so closer to the eruption time period, I have mentioned as the stage 1 eruption. So I'm going to mention the variable stage 1 eruption is equals to earth engine dot image collection Copernicus similar, and I'm going to mention the date is to be around 2025 November 2 to 2025 November 24. And I'm going to select this particular band, column number density, and apply median function. And last, we're going to visualize the post eruption equals to, and it's going to mention as a median function. And in the next step, we're going to define another variable called post-eruption is equals to Earth Engine.image collection Copernicus S5P offline L3 SO2, and we're going to apply the filter function dot filter date 2025 November 26, and the end date is going to be 2025 November 30, and we're going to select the specific band called SO2 column number density using dot select SO2 column number density. And last, we're going to apply this median function, is dot median function, so to acquire a median image for the specific timeline. And last, we're going to add this layer, so using a map dot add layer pre-eruption SO2 vis params, and output the layer as pre-eruption SO2 November 1 to 12. And similarly, so to add the stage 1 eruption, we're going to mention map dot add layer stage 1 eruption SO2 vis params, output the layer as stage 1 eruption SO2. And last, to add the post eruption, we're going to mention SO2 vis params post eruption SO2 from November 26 to 30. And we have to mention one more thing, that this particular data has a revisit period of 2 days. So every 2 days we're going to get this image for this study area. So it's going to cover the entire globe. So the revisit period is around 2 days. So let us take a look at this image here. Let me run this code. So I'm going to click this option called run, and it's going to run the code. So here we are currently visualizing the eruption which took place on November 25 here. So let us visualize the pre-eruption here. I'm going to turn this layer. So this is the condition before the eruption here. So during October, this is the condition of this particular volcano. I can able to see. Let me turn to a satellite mode. So this is the condition here. You can able to see. Let me turn this off, and let us visualize the pre-eruption here. So here you can able to visualize before, during, in October. This is the condition of this particular volcano in October. And let me show you here the stage 1 eruption, which is from between 18 to 24. And here you can able to see the eruptions has started here. The plumes has traveled here, the sulfur dioxide. You can able to see that. And the post eruptions. So let me turn on the post eruption. So here you can able to visualize this particular one. This is the pre-eruption stage of sulfur dioxide. You can able to visualize this is the volcanic area here. So you can able to see this red dot, so which indicates this our study area. And this is the precondition. And next is stage 1. So this is the stage 1 condition where the volcanic erupts and the plumes moves towards the northern part. And the post eruption of sulfur dioxide. So let us visualize it. So here you can able to visualize this particular one here, the post eruption here. So there is a very high level of sulfur dioxide has been ejected from this particular volcano here. So you can able to clearly able to visualize this concentration of sulfur dioxide in this area, as well as it travels towards the India here. You can able to see. Let me turn this off here. I'm gonna turn this off, and here you can able to visualize it. Let me turn this on, and let me adjust the transparency here. Gonna adjust the transparency, and now we can able to see the movement of this particular one. So it travels from Ethiopia, as well as it moved towards south towards northern Sudan, and you can able to see the movement here. And it moves towards the Oman, and it moved towards India here. You can able to see towards the northern states here. So these are the states where this plumes, this particular sulfur dioxide gas has moved. So you can clearly able to visualize it here from this image. So this is the precondition, and this is the buffer area here. So let me increase the transparency of the buffer region. So this is the buffer area, you can able to see, and this is the precondition, and this is stage 1, and this is the post after the eruption. So you can clearly able to visualize this travel of the sulfur dioxide. So the next step we're going to mention is we're going to add some legend to a map layer. So to visualize the color, visualize the concentration of sulfur dioxide in different colors based on its concentration, that is molecules per meter square. So for that, we're gonna add a legend. So for that, we defined a variable called legend is equals to UI dot panel. The style I'm gonna mention is the position. It's gonna be the bottom right. I'm gonna place my legend at the bottom right, and the padding it's gonna be 8px and 15px. And the variable we can define another variable called legend title is equals to UI dot label. So we're gonna mention the legend like this here. You can able to see this legend. We mentioned as sulfur dioxide concentration in molecules per meter square, and the style and the font weight we're gonna mention is bold, and the font size it's gonna be 14, and the padding and margins you can fix this different according to your choice. And next is the variable legend items. So each of the concentration is going to be highlighted in different set of colors here. For example, the black, it's going to be a zero, percentage of zero molecules per meter square of sulfur dioxide, and the highest it's going to be yellow, and greater than that it's going to be in red color. So you can see that from this image here. And next is to add the legend. We're going to mention is legend dot add legend title. And the legend item dot for each function item, we're going to mention the variable color box equals to UI dot label, style the background color, the item color, and the padding and margins. Similarly, the variable description is equals to, we're going to define a variable called description is equals to UI dot label, and the value is going to be item dot label referring to this particular one. And the style, it's going to be, we're going to mention the margin of your choice, and the row, the variable for row, we're going to mention the variable row is equal to UI dot panel, the negates, the color box and descriptions. So likewise, you can add a variety of customization to your legend. And last, to add the legend, we're going to mention map dot add function. In that, we're going to mention the legend. So it's going to represent this particular variable where we created here. Let me show you that, the variable legend. So now let us run this code and again visualize the result here with the legends. Let me turn to satellite mode, and let me zoom out here. So this is the volcanic site here, and you can clearly able to view the travel of this sulfur dioxide. And last is we have to navigate to this option called task sections here, and in that we have the set of tasks here, starting with the unsubmitted task. So to export the sulfur dioxide concentration as a CSV, so we have to click this option called sulfur dioxide time series 2025. We're going to click this option, and to export, we're going to export to drive or a cloud storage. It's according to your choice. So in my case, we're going to export to cloud storage, that is Google Drive, and the drive folder and the full file name and the CSV. And I'm going to click this option called run to export this particular to our Google Drive. And similarly, we have all the mean sulfur dioxide image for this particular year 2025, and the anomaly has took place in the November here. So we can able to see the SO₂ sulfur dioxide November 2025. This is the period where the volcanic eruptions has taken place. It's gonna give us a mean image. And to export any image of your choice, for example, I'm gonna export this particular one, sulfur dioxide November 2025, for the specific area, the buffer area of this particular one here. To export that, so what I'm gonna do is I'm gonna mention is I'm gonna navigate this option, click run, and it's gonna task name is sulfur dioxide November EPSG4326. It's a coordinate reference system, and the spatial resolution is 1113. And we're going to export to a drive, that is drive folder is GE SO₂ analysis, and the file name is going to be SO₂ November 2025, and the file format is GeoTIFF. So now to export this image, we're going to click this option called run to export this image. So we're going to click this option called run to export this image to my Google Drive. So it's going to export this image, and we have this submitted task called so it's going to take some time to export this image to your Google Drive. So next I'm going to navigate to the top section. So in this video, I have shown you how to estimate the sulfur dioxide concentration from Ethiopic volcanic eruption using Sentinel-5P imagery in Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like. And the image got exported here. You can able to see the image is got exported, and you can download from your drive here. So thanks for watching, and make sure that you subscribe to our channel and give us a like.